In this video, we are going to explore the concept of hotspots. Okay, so first of all, let me give you a premise about why hotspots are there as a concept in plate tectonics. So, first of all, if you recall, we can create islands, right? We can create volcanoes. We can create all of these geological features because of interaction of plate boundaries, right? When two plates collide and it's continental, you create mountains. If it's continental oceanic, you create trench and land volcanoes. If it's oceanic, you create trench and you create underwater volcanoes, which become volcanic islands. And if it's divergence, you can create a rift valley if it's in a continental plate. And then that rift valley would develop into Great Lakes, would become into a small sea and then an ocean. And then when you have divergence in an oceanic plate, you would have an oceanic ridge, which would create new seafloor and spreads the seafloor and so on and so forth. So almost all of these geological features are explained by plate boundary interactions. However, there are some exceptions. Okay, if you remember our distribution of earthquake epicenters, mountain ranges, and volcanoes, although most of them fall near the boundaries because earthquakes, mountains, and those things are created because of boundary interactions. Some of them do not fall near any boundary. Okay, and one of the most um, prime example of this is Hawaii. The Hawaiian Islands are a group of islands that is volcanic in nature. Okay, so let's explain what that is. Hawaii are a series of volcanic islands, right? And the key word here is volcanic islands. And again, how do you create volcanic islands? Well, you have the ocean floor. This is the water here. You create underwater volcanoes, right? And then these volcanoes spew out materials, more materials, more materials, more materials, and then until they poke out of the water and create a volcanic island. Now, that is a problem conceptually because if you look at Hawaii, it is in the middle of the Pacific Ocean. It's nowhere near the boundaries, right? It's in the middle. So, how can you create a volcanic island when volcanic islands require volcanoes to be created and volcanoes require plate boundaries, right? Now, the Philippines, Japan, has a lot of volcanic islands, and that's understandable because, again, we understand that when two plates collide, oceanic and another oceanic, this oceanic plate subducts under the other, forms volcanoes here, which are underwater first, and then they develop and become islands. So obviously, you can bet that these islands are near the boundary. In fact, if you look at the Philippines, again, imagine the Philippines was not there yet, then this boundary between the Philippine Sea Plate and the oceanic part of the Eurasian Plate, that boundary would have been responsible for the creation of the majority of the islands of the Philippines. The same thing as Japan, because Japan is near the boundary between the Philippines, the Pacific, and the Eurasian plates, right? But Hawaiian Islands, that's kind of an outlier because it's not near any boundary, right? So scientists took note of that. They took note that there are some phenomena, some geological features in the Earth that cannot be explained by plate boundary interaction. Because remember, most of the geological features are explained by plate boundary interaction. Okay? So, because of that, scientists kind of went back to their concepts of plate tectonics. And again, the driving force for plate tectonics are the convection currents, right? Convection currents. Okay? And again, if you remember, the convection current works by, again, this distribution of heat, right? So if you have a pot of water, what happens is the stove supplies heat onto one side, and then Because of that, this side becomes hotter than the rest. And because of that, the materials here rise up. And because the heat source is here, when it's far away from the heat source, it cools down. So it would sink back down. But again, it cannot go back to the same direction because materials are coming up. They will collide. So they will instead sink back down, but to the sides. And again, it creates this convection currents. Okay? So therefore, if you think about it, convection currents are created because there's an uneven distribution of heat. This one is hotter. This one is cooler. So what happens is the hotter material floats up, the cooler material cools down. Sinks down, and then you create these convection currents. So now that begs the question, sir, what if instead of heating this part, what if I also heat this part? Well, if you heat that part, meaning both sides are now hotter, are now hot, right? So you can argue that, sir, in that case, heat will not travel anymore because this is hotter and this is hotter. Well, it still, because at the center it's still cooler. So what happens is you will just have a convection current that will be similar like this, right? And so again, you can argue, sir, what if I'll just make the temperature I'll make the temperature of the fluid the same all throughout. Okay? Meaning, I don't know how you would set that up, but what if the temperature of the fluid is the same all throughout? There are no places there that are hotter than the other. Well, in that case, you won't have any convection currents because convection current is about heat transfer. Remember, heat transfer only occurs if you have two things that have different temperature, right? If one is cold, the other is hot, heat will always flow from the hotter material to the cooler material. But it will never do the opposite case. It's one of the tenets of thermodynamics. But the point is, you need to have difference in temperature. If there's no difference in temperature, there will be no heat distribution. Then therefore, there's no heat transfer. And remember, convection current is just a method of heat transfer. So if there's no temperature difference, there's no need to distribute energy, distribute heat. So therefore, there's no convection currents, right? So, if you're wondering, okay, so this is the Earth, sir. The core is the hottest, so this is the heat source. So if this is the heat source, sir, it will distribute heat outwards, right? Just like the stove, it will distribute heat towards the upper layers. Yes, but another concept in thermodynamics is I'm paraphrasing this. I'm making this simpler. I'm making this high school level. But again, you must be aware that sometimes when you simplify concepts, it ruins. It loses accuracy. But in this case, it can't be helped because I could not do a session explaining thermodynamic concepts to high school students just so that we can understand this concept. But in a gist, thermodynamics tells you that no matter what you do, when you have a heat source, that heat source will never distribute evenly. Okay, let me repeat that. According to thermodynamics, again, this is paraphrased, so it's a little bit inaccurate, but it captures the essence of the concept. It tells you that heat will never distribute evenly. Okay, let me get that straight. Heat will never distribute evenly. So another way of explaining that is, if you have an iron ball, okay, and let's say you try to heat this iron ball by a stove, right? So obviously, if you do that, this part will be heated first, and then the other part would be cooler. Now the heat would try to distribute, but again, it will still be uneven because this part is hotter than the rest, right? So what you can do is you can kind of try to rotate that iron ball every now and then to kind of distribute the heat. But again, thermodynamics concepts would tell you that no matter what you do, heat will never distribute evenly. And that is tied to the concept of entropy, which is chaos, the concept of chaos theory. So, meaning systems are always inherently chaotic. So therefore, even if the rules of heat distribution is simple, it will never heat will never distribute evenly through the surface of the iron ball. Okay. So again, that's kind of heavy. You need higher senior high school, college level understanding of thermodynamics to kind of really understand that. But again, just take it at just please believe what I say, that thermodynamics actually postulates that heat will never distribute evenly through a certain material because of chaos and entropy, right? So what's my point? My point is, if you have a material, you heat it, yes, heat will distribute because of conduction, convection, and radiation, but it will never distribute evenly. Meaning, if you take the temperature of that material, some spots will always be colder, some spots will always be hotter than the rest. Okay, let me get that straight. Heat will never distribute evenly, such that some spots will always be cooler and some spots will always be hotter. And there some and others would always be kind of the average, but some will be colder, some will be hotter than the rest. Okay, that's a thermodynamic concept. Okay, so what's hotspot? Well, it's from the name itself. It's a spot, meaning it's a point. It's a particular place that is hotter than the rest of the locations. So a point in what, sir? A point in what? A point in the asthenosphere. So this is the concept of hotspots. There are certain spots in the asthenosphere that are just hotter than the rest. Now, don't get me wrong. Obviously, the lithosphere, and then below that is the asthenosphere. We know that the asthenosphere is inherently hotter than the lithosphere. So the asthenosphere is made up of molten, semi-melted, fluid-like materials, right? So obviously, this layer is hot. But the hotspot concept tells you that there are certain points, certain places, certain locations in the asthenosphere that are inherently hotter than the rest because of thermodynamic properties. Okay, because of thermodynamics, it's inevitable that there are certain spots in the asthenosphere that are hotter than the rest. Okay, now if you know about sunspots, it's kind of the similar thing. In the sun, there are certain spots in the sun that are colder, so it's kind of opposite. In the sun, there are spots that are colder than the other spots, or cooler than the other spots, and a lot of it is some of it is because of thermodynamics, but some of it is because of the magnetic field in the surface of the sun. But the point is, it's kind of the similar template. If you have sunspots in the surface of the sun, there are also hot spots, but on the asthenosphere of the Earth. Okay, so that's it. A hot spot is simply a point in the asthenosphere that is hotter than the rest of the asthenosphere. Okay, so I know that's a long explanation, but I need you to understand why hotspots are there and what's the concept behind hotspots. Now that we have established that it's a spot, it's a point that is hotter than the rest, now let's ask ourselves, okay, so what? So what if there's a place in the asthenosphere that is hotter than the rest of the asthenosphere? So here's the thing. Normally, the lithosphere is obviously on top of the asthenosphere. Now, remember, the asthenosphere is fluid-like, it's melted, it's hot, relatively to the lithosphere, right? But it's not hot enough to melt the lithosphere. Okay? Let me get that again. Let me say that again. The asthenosphere is molten, but its temperature is not hot enough to melt the lithosphere. Normally. Okay? So, normally, this fluid molten material will never come out of the lithosphere because it's not hot enough to melt the lithosphere. So, that's why you have to have convergent boundaries, places where one plate subducts under the other. And because of this, the crustal material here gets melted, it bubbles up. And remember, crustal material, crust is less dense than the asthenospheric materials in the bottom. So those crustal materials melt, and then they punch through the lithosphere. But normally they don't. Normally the asthenosphere on itself will not penetrate, will not breach the lithosphere. It's only because of convergence that the asthenosphere or melted materials from the crust can kind of breach through the lithosphere. Okay? That's the premise. But remember, a hotspot is a point in the asthenosphere that is abnormally hotter than the asthenosphere. So how do we define abnormally hotter? It means that these spots are hot enough to melt the lithosphere. Okay? So let me get that straight. The asthenosphere is normally not hot enough to melt the lithosphere. But there are particular spots in the asthenosphere that are just hotter than the rest of the asthenosphere, that these places, these spots, melt the lithosphere on top of it. Okay, it melts the lithosphere on top of it. And therefore, if it melts the lithosphere on top of it, therefore it can create volcanoes. If it's underneath the ocean, it can create islands, and so on. Okay? Now, I know what you're thinking. If you learned divergent boundaries before, you would kind of say that this is similar, sir, because the asthenosphere is hot, and because it's hot, it melts the lithosphere here. How different is that from the concept of divergence, where you have two plates and you have a convection current? And remember, in this convection current is moving up. And if you think about it, why are the magma materials here moving up? Well, because they are denser. And why are they denser? Because they are hotter. So these materials are hotter than, say, the materials here. That's why it's rising up. So if this part is hotter than the rest of the asthenosphere, isn't that just a hot spot? I mean, the concept is similar, sir. This is just a column of magma rising up. The fact that they're rising up, meaning they must be hotter than the rest of the asthenosphere. So therefore, isn't that a hot spot? Yes and no. Yes, in the sense that it's a spot that is hotter. Yes, and it rises up. But it's not a hot spot in the sense that because it created a crack here. Because it creates a crack, now you can argue that the magma materials come out not because they have melted the lithosphere, but because there's already a crack there. So therefore, the pressure is just moving out, and it's not really the heat from that rising column of magma that melted the lithosphere. In hotspots, you really find places where there is no boundary, there is no crack, and yet the lithosphere is melted. Okay? So again, I hope you understand the difference. In this case, hot materials come out, but because there's already a crack, there's a oceanic ridge, magma forces its way out of the crack, but still it's a hotter spot, just like this. But here, you have an oceanic ridge, and therefore, the magma comes out not because the lithosphere is melted by the heat, but because there's already a crack there. Here, it's really different because there's no boundary. It's simply that that particular part is hotter, that it melts the lithosphere. Okay? Now, if you really think about this, you can then argue, sir, you would now then argue that, sir, what if I have a plate and then I have a hot spot underneath this plate, so it melts this part, and then another hot spot here that it melts this part. Because of that melting, it weakens the lithosphere, sir. So if it weakens the lithosphere, wouldn't they create a crack and kind of connect the two hotspots together, create a crack, and now you create now a divergent boundary. So the point is, isn't it that hotspots initiate the divergent boundary? So ultimately, pareha nila, sir. The divergent boundary is kind of like the same as the hotspot. Well, yes, there's a reason to believe that it might be the case. It might be that it's really hotspots that kind of initiate the plate to diverge into two, and then now you create a divergent boundary. That is true. But as it stands now, what we really call hotspots are places where the lithosphere is melted and then you don't really see a boundary. Okay? So in a sense, again, there's ambiguity in defining what a hotspot is and what is a regular upwelling of magma. It might be that these two are similar. It might be that it's just the result that's different. Maybe if the upwelling of magma only melts the lithosphere and doesn't create a hotspot, doesn't create a boundary, it's called a hotspot. Maybe when it upwells and it creates a boundary, because the pressure is released, it's not hotter anymore, so it ceases to become a hotspot and we just call it a boundary, and we just call it part of the convection currents. Or maybe it still remains a hotspot even with the boundary there, right? So again, in science, there's no definitive definition for everything. All of these things could be connected, but understand that that's what hotspots are. In some places in the asthenosphere, the magma material is hotter. And why are they hotter? It might be because of a convection current. And such that they melt the lithosphere on top of it. Okay? So, if I pull out here a map of the hotspots in the world, one of that hotspot is Hawaii. Okay? And again, just to reiterate on what we discussed, sir, look at this. Iceland has a hotspot. Here, in the middle of this oceanic ridge, there's a hotspot. So maybe again, sir, it's the hotspots that initiate the breaking of a plate, creating a boundary, right? And maybe when the crack opens, because the pressure is released, the hotspot ceases to be a hotspot anymore because it's not as hot as when it did not have any outlet, right? When the crack was not created. So maybe some of these hotspots initiated the divergence and then they ceased to be hotspot. But clearly, there are also places where hotspots are in between the boundary. So maybe some hotspots initiate the divergence of two plates, but even after the divergence of two plates, that spot still remains a hotspot, meaning it's still unusually hotter than the rest of the asthenosphere, right? So again, there's no definite distinction between whether it's a hotspot that is just not in the boundary, or whether the hotspot created the boundary, or when the boundary is created, will the hotspot cease to be a hotspot, or is it still a hotspot but it's in the boundary itself? Okay, so you have to understand that. In fact, if you look at Africa, remember East Africa? Remember we said that the east of Africa is kind of diverging away from mainland Africa, and right now you see rift valleys and Great Lakes there because it's starting to break apart from the Africa. Look at it. There are two hotspots near it. So it might be that again, it's the hotspots that initiated the breaking up of this part, and we are just in the early stages. Later on, when this becomes a fully fledged boundary, maybe the hotspots would have an outlet, and therefore they wouldn't be as hot as they are now, and the hotspot disappears, and now we don't see the hotspots. That's why we cannot pinpoint if it was created by hotspot or not. Or maybe that hotspot will persist even after the boundary is there. So again, who knows? But the point is, hotspots are these places in the asthenosphere that are hot enough to melt the lithosphere above it. In some hotspots, it melts the lithosphere above it and it doesn't create a boundary. In some hotspots, the hotspot actually triggers and creates the divergent boundary. And in some hotspots, when the boundary is created, the hotspot ceases to be hotspot anymore because maybe it has an outlet already of all of that heat. In some cases, even when the boundary is created, the hotspot is still there. But essentially, that is what a hotspot is. It is a particular point in the asthenosphere that is hotter than the rest. And again, why would it be hotter than the rest? It's because of thermodynamic properties related to chaos and entropy. When you heat something up, the heat will never distribute evenly to all parts of the fluid. So some parts of the fluid will always be hotter than the rest. And therefore, you have these hotspots. Okay? In the next video, we will explore what hotspots do when they are underneath the oceanic floor and what hotspots do when they are in the continental crust, underneath the continental crust.